All right, everyone. In this video, we are going to talk about the rules for gauging resonance structure stability. So let's say that you're given a few contributors and you're asked to rank those from least stable to most stable. The first thing that we want to gauge is if atoms are full octet or incomplete octet. The ideal is having full octets. Let's do that first. Structure A is full octet. The nitrogen is full octet because it's got a total of 8 electrons around it. So there's 2, 4, 6, 8 electrons around it. We count each bond as 2 electrons when we're gauging octets. The next contributor is also full octet. Oxygen is a full octet. All the atoms are full octet. But C is incomplete octet because we have a carbon of positive charge. All carbons of positive charge will be incomplete octet. So that's automatically the least stable. C is the least stable. Now that A and B have the same octet status, we'd move on to our second level of consideration, which is charge accommodation. That is to say, how well do they stabilize the charge? Here's a little guide down below. Remember, when you're gauging the stability of a charge on atoms that are in the same periodic row, like nitrogen and oxygen, the factor that we'd use to differentiate their stability would be electronegativity. A same row comparison requires electronegativity, but in certain cases, you'll look at a same column comparison, like maybe oxygen to sulfur. In the same column, we would use size as our metric as opposed to electronegativity. Now, if we have an overall positive charge there, we'd ideally want that on the less electronegative atom. Nitrogen is less electronegative, oxygen is more electronegative. So in this case, the nitrogen is going to bear that positive more stably than the oxygen given its lower electronegativity. A is more stable than B. Now, if we were looking at a negative charge, notice that oxygen negative would be more stable than nitrogen negative. A more electronegative atom balances a negative charge better, but a more electronegative atom would balance positive more poorly. Less electronegative atoms balance the positive better, with the exception, of course, of carbocations, which are incomplete octet atoms. So let's now look at the next example. Starting with octets, A has a carbocation, so therefore we know that's automatically incomplete octet. B has all full octets, and C also has full octets. So right away, we'll say A is the least stable. Then between B and C, we're going to have to do another additional consideration. That would be charge accommodation. But what we're going to notice is that B is overall neutral and C is charged. Now, if you're comparing something that's neutral to something that's charged, the one that's neutral is going to be more stable, because usually having charge leads to a higher energy state. So again, to recap that, we looked at octet status that made A the least stable, and between our full octet structures, one was neutral, and that inherently made that more stable than the one that was full octet and charged. All right. Now, looking at this next example, there's a lot going on, kind of a lot for our eye to digest. So what I'd recommend doing first and foremost is seeing how they're similar and then how they're different. What appears to be consistent between the three structures is this N positive O minus, and then what's different would be having an O minus there in A, an N minus in B, and then an O minus in C. Tracking with you, each of these structures possesses a full octet. None of these are incomplete octet. So we would go on to charge accommodation. Based upon charge accommodation, we're now looking at the negative. So the more electronegative atom, oxygen, would balance that negative charge better than the nitrogen. The nitrogen balances it more poorly given its lower electronegativity. Therefore, in this example, B is the least stable. Now, between A and C, because their octet status tied, they're both oxygens bearing the negative, we now need to move on to the third rule, which is minimization of charge separation. If we look at the left side of your screen here, and we think about energy, when you have a positive and a negative closer to one another, just spatially, they will be lower energy than a positive and negative that are further apart. When you have a positive and negative further apart, they're not going to be able to balance each other as well. But if they're closer to one another, they counterbalance each other. Positive stabilizes negative. So looking at A, this oxygen appears to be pretty far away from that nitrogen positive, and in C, the oxygen negative is closer to the nitrogen positive. Given that that oxygen is closer to the positive is stabilizing that negative, and that would make C more stable than A. A is higher energy than C because the positive and negative are further apart. Now, it's really important that we analyze in that order. Look at octet status first, then charge accommodation, and then if need be, minimization of charge separation. Going back to the first two examples, in that first example, we looked at octet status, said C was the least stable, but then between A and B, because they had the same octet status, we went on to charge accommodation. And based upon charge accommodation, we could differentiate A and B, therefore we didn't need to get to minimization of charge separation. In the second example, we said A was the least stable because it was incomplete octet. Then B and C were both full octet, so we had to move on to charge accommodation. Here, we had that difference of neutral versus charged. So again, we didn't get to minimization of charge separation. That wasn't relevant. But for 3, they were all octets, all possessing full octets. So we had to move on to charge accommodation. That led us to say that B was the least stable because nitrogen's less electronegative than oxygen. But between A and C, they had the same octet status. The same atom was bearing the negative, both oxygens. So we did have to move on to minimization of charge separation. The order of analysis is important. All right. Then the last one we'll do in this video is the top one here on page 10. First thing that we're going to do is look at octet status. Tracking with you, A appears to be all full octets. B, we have a carbocation, so that's incomplete octet. C has all full octets, and D has all full octets. Right away, we're going to say B is the least stable because it's incomplete octet. Now looking at A, C, and D, which are all full octet, I'm noticing that D is full octet and neutral, whereas A and C are full octet charged. That means that D is more stable than C and A. Then when I'm gauging C and A, I have to look at charge accommodation. There I'm seeing a nitrogen positive versus sulfur positive. Looking back at our kind of cheat here with charge accommodation, notice that nitrogen positive is more stable than sulfur positive. C is more stable than A. Now, sulfur is larger than nitrogen. It's also larger than oxygen. And large atoms balance positive charges poorly because that's a larger valence area of deficiency. But if we're thinking about, say, a large atom bearing a negative, large atoms can disperse that negative well in the larger valence shell. I'm going to repeat that. When we're looking at large atoms, a large atom would stabilize a positive poorly compared to an atom that's smaller. That's what we're looking at here with sulfur and nitrogen. Nitrogen was smaller. It balanced that positive charge better. But if we were looking at a negative charge, a larger atom would balance that negative better because it can disperse it over its larger valence shell. Okay. That being said, it wouldn't hurt to memorize this ranking and then rationalize that using size and electronegativity trends. All right. That being said, this concludes this video on resonance structure stability. Definitely be poised and ready to approach a question like that on your exam. And we kind of hinted at that when we went through these resonance structure examples, looking at some where we gauge the stability. You can go back, and if you want, you can try to look at which one is most stable, which one is least stable by applying those factors that we just talked about.